Hello everyone, in today's video I'm going to show you how you can generate precise delay with the help of timers in STM32. So the board that I am using is STM32f405, but the settings will be more or less similar for all the STM devices, or at least for F4 series. So I've already written the program. I'm not going to waste your time by writing the program in the video. I'll just explain the program. So what I've done in this program is I've used two timers, timer 2 and timer 3, and with the help of these timers I'm increasing two variables, count and count 1, at different delays. So here you can see I have created three variables, count, count 1 and main count. As I said, count and count 1 are increased by timer 2 and timer 3, and main count is a variable which is getting increased inside main function in while loop. So why I've used timer 2 and timer 3 is I wanted to use two timers because in STM32 we have 16-bit timer and 32-bit timer. So I wanted to demonstrate this program on both 16-bit and 32-bit timer. So that's why I've used timer 2 and timer 3. So if I go to my reference manual, you can see in this STM32f405 device, timer 2 is a 32-bit timer and timer 3 is a 16-bit timer. So that's why I've used two timers. So now I'll quickly start explaining this program, what I've done and why I've done. So before using anything in general, we have to enable the clock for any peripheral. So here I'm enabling clock for timer and GPIO port. I'm enabling clock for GPIO port because apart from increasing count and count 1 variable, I'm also toggling an LED inside the timer function with the help of a timer. And I'm doing that so that we can see our output in the logic analyzer window. So here I have a logic analyzer connected and we'll see the output. So the first line that I'm writing, these two are for enabling the timer. So you can find the bus to which your timer is connected with the help of your data sheet. So this is my data sheet right here. I can go to description and functional overview. You will see I'm using timer 2 and timer 3, which is here, and they are connected to APB1 bus, which means I have to use APB1 ENR enable register to enable timer 2 and timer 3. So if I go to RCC APB1 ENR, which should be somewhere here, here it is. So these are the two bits that I have to enable or write one to it in order to enable the clock for timer 2 and timer 3. And that's what I'm doing here. I'm writing 1 in 0th and first position. Then I'm enabling the port. Similarly, you can find bus for GPIO port. In my case, I'm using GPIO, uh, it is GPIO B and GPIO C port. So this is for GPIO B and this is for GPIO C port. I'm enabling both of these ports. Then I'm setting both of the pins. So the pins that I'm using are PC6 and PB15. So I'm setting both of these pins as output. Okay, I'm not setting O speed R, O type R, because the default values that are there in the microcontroller are enough for me to show this or demonstrate this program. Next, we can start writing the values to ARR and prescaler. So this is timer 2, which is a 32-bit timer, which means inside ARR, I can write a 32-bit value. Okay, so I have written 16 million here. Now I'll explain why I've written 16 million here. But first you need to keep in mind, if you want to write, if you're writing any value in a 32-bit timer, the value can be of obviously 32 bits. But if you're writing in timer 3, which is a 16-bit timer, then you have to write a 16-bit value. So ARR is basically the maximum count up to which my timer 2 will count, starting from 0. So in my case, timer 2 will start counting from 0. It will go up to 16 million. Okay. Now why I've chosen this 16 million specifically is because by default, my timer is using HSI. It's using HSI clock, which is high speed internal clock. And this clock is of 16 megahertz, which means uh, I'm receiving 16 million clock pulses. I'll just write 16 million clock pulses in 1 second, which means my timer will count up to 16 million uh, in 1 second. Okay, so each counting takes one clock pulse. So if I want to generate delay of 1 second, I can put 16 million here and it will generate a delay of 1 second. That's why I've written 16 million here. Okay, in timer 3 I can't write 16 million, right, because it is a 16-bit timer. So maximum value that I can write is a 16-bit value, that is around 65,535, something like that. Okay, sorry, this is not the ARR value, this is my ARR value. Okay, so I have written 500 in ARR value. And I have used prescaler register, which is basically like a frequency divider to decrease the this clock frequency that is coming to timer 3. So by default, as I said, timer will use HSI, which will give 16 million clock pulses in 1 second. And I have used prescaler value of 16,000, which means 16 million will get divided by 16,000, and the resulting frequency that reaches to my timer will be 1000 or 1 kilohertz. Okay, I'll just write 1000, which means it will count up to 1000 in 1 second. It will count up to 1000 in 1 second. And in ARR, I have put 500 because I want to generate half second delay, or you can say 0.5 second delay through this timer 3. So from timer 2, I'm generating a 1 second delay, and from timer 3, I'm generating half second delay. So I've written 500 because I want to generate 0.5 seconds of delay. For example, if I wanted to generate, let's say 1 second of delay from this timer 3, I would have written 1000 here. If I wanted to generate a delay of 2 seconds, then I would have written 2000. Similarly, for 3000, 4000, I can write like this. But you have to keep in mind this ARR value will be maximum of 65, will be maximum of 16 bit, which is 65,535. So through this timer, I'm going to generate delay of half seconds, and for this, I'll generate delay of 1 second. Now, after writing ARR and prescaler values, I'll set UG bit, that is update generation bit, inside EGR register. So I'll show you in the reference manual. Inside timer, we have a register called EGR. So this is our EGR register, and we have UG bit, update generation bit, in this EGR register. So when I set it as 1, it reinitializes the counter and generates an update of the register. So basically, it reinitializes the value of the timers, counters. Okay. So that's what I'm doing here. I'm reinitializing the values of this timer 2 and timer 3 with the help of this UG bit. So I'm setting UG bit for both timer 3 and timer 2. So next step that I'm doing here is I'm enabling an interrupt. So for enabling an interrupt, again, we can go to a register called DIER. So this is DMA slash interrupt enable register. Inside this register, we have a bit called UIE, update interrupt enable. So when you set this bit as 1, it enables an interrupt when there is an update condition. Update condition is basically when your ARR value overflows. Overflows means it reaches the this ARR value. Okay. So when your timer counter starts counting, it starts counting in a value in a register called CNT register, count register. So I'll show you that register. This is the count register. So when my count register reaches this ARR value, 500 or 16 million in case of 32-bit timer, in our case, it will generate an update condition. And if I have set this UIE bit, update interrupt enable bit, that is in DIER register, if I've set this bit, then I'm basically enabling an interrupt every time my timer counts up to ARR value, 500 or 16 million. So this will enable an interrupt, okay, which will generate an interrupt every time my timer counts up to ARR value. So this is what I'm doing here. So I'm doing it for both timer 2 and timer 3. Next, we have to enable interrupt from NVIC side. NVIC is Nested Vector Interrupt Controller. It is in Cortex M4. This is basically a hardware module which manages all the interrupt inside the Cortex M4 microcontroller. So if you want to enable these interrupts, you have to enable it from both timer side and NVIC side. So this is a function, NVIC enable IRQ, which is inside your core Cortex M4 header file. So I'm using this enable IRQ function to enable the IRQ. This IRQ is basically my interrupt request number. So again, this is defined inside the header file. So IRQ number is 28 for timer 2. I can directly write 28, or I can use this macro. Similarly, for timer 3, it is 29. I can directly write 29, or I can use this timer 3 interrupt request number macro. So that's what I'm doing here. After that, I'm just enabling the timer with the help of CEN bit, which is inside CR1 register, control register 1. So this is CEN bit, which is counter enable bit. So if I go to CR1 register, this is CR1 register, you'll see CEN bit, counter enable bit. So after doing all my settings, I can enable the counter and it will start working. That's it for the program inside the main function. Now we have to write the handlers for these interrupts, because now we know our timer will generate an interrupt after every 1 second or half seconds. Okay, for timer 3, it is going to be 1 second. Sorry, for timer 2, it's going to be 1 second, and for timer 3, it's going to be half seconds. So now we have to write a handler for the interrupt that is going to be generated by this timer 2 and timer 3. So this is the handler that we have written. So in this handler, as you can see, whenever timer 2 uh, exceeds the ARR value, I'm going to increase the count value. Count is a variable that I've declared. Okay, so this is the variable that I'm going to have declared, which means count variable will increase or increment after every second. So uh, for every second, it will increment by 1. And this is, as I said, I'm using two LEDs for the output to show in the this logic analyzer. I'm using two GPIO pins. So these are the GPIO pins I'm using, PC6 and PB15. So I'm doing nothing but toggling the PC6 output pin. And then inside the SR register, that is status register, you have to clear a flag. So if I go to SR register, this is status register. Here we have a flag, update interrupt flag. So every time my timer generates an interrupt, this flag will be set. So this flag will be set every time an interrupt is generated. And after handling the interrupt, after executing the subroutine, we have to clear this flag to basically tell microcontroller that interrupt has been processed. Now we can continue with the program that we were executing, basically our while loop. It's same for timer 3, just I'm incrementing a different variable, I'm toggling a different pin and clearing the flag from timer 3 status register. So now we can see the output of this program. So to see the output, I'll upload this program. Now my program is getting uploaded, and this is my logic analyzer device. And in my logic analyzer, I have connected channel 0 and channel 1 to timer 2 and 3. So what I can do is, first I'll put this in debug mode to see our variables, whether they are incrementing or not. So these are our variables. I have already imported these variables. Now when I run this program, you'll see count variable increases after every second, okay? Whereas count 1 increments twice in a second because the delay is of 0.5 seconds. And main count continuously increases because it is inside this while loop main function, okay? Now to check the accuracy of the delay that we have created, we can see it in uh, our logic analyzer. So now I've connected my pins to the output of the board, that is PC6 and PB15. Now I can start my logic analyzer and then we can see the output. So channel 0 is where my 1 second delay is getting generated, and channel 1 is where I'm generating half a second of delay. So I can stop this and we can measure this delay. So you'll see this delay is 995.31 milliseconds, which is very close to 1 second. So obviously it's not exactly 1 seconds, but this is very, very accurate. If I want to make it more accurate, then I can change my clock source from HSI to probably HSE or something. But I feel for most of the application, this might be enough. The accuracy might be enough. Similarly, for this delay, you can see the delay is of 498 milliseconds, which is very close to 500 milliseconds or half a second. Okay. So now I will change the value of ARR to see the effect in our output. So as I had said, if I change this to 1000, the delay will be of 1 second because the frequency is 1 kilohertz or 1000 hertz. Similarly, if I change this to, let's say, 3000, then the delay should be of 3 seconds, right? So I'll upload this program. Now our channel 0 will be generating delay of 1 second, whereas channel 1 will be generating delay of 3 seconds. So again, I'll go to logic analyzer. I'll start the sampling. Now you can see channel 1 is generating 3 seconds of delay. I can stop this. Now you can measure this delay. It is 2.98 seconds, which is very accurate. So this is it for this video. I hope you liked it, and thank you for your time.